Hello, my name is Mohamed Tarek, and I'm a scientist at Puma's AI. And today I'll be presenting to you my work on Nonconvex.jl, which is a constrained non-convex optimization toolbox in Julia. So before I go on, let me first introduce my company, and let me say that we're hiring interns. So if you're interested in applying optimization for or in healthcare delivery and healthcare systems, then please get in touch with me and we can talk some more. So in Pumas, we engineer solutions that empower those on the front lines of healthcare from discovery to delivery. So we have two main products, Pumas and Live, that support every step of the way of analysis and decision-making of data in the clinical trial space and in the drug development and delivery space. So if you're interested in any of this and applying optimization to design clinical trials, get in touch with me and there might be some opportunities. So with that, I will leave you to the rest of the presentation, which I pre-recorded. So thank you. Enjoy the presentation. Basically, there are four main emphasis or unique features of Nonconvex.jl, I guess, compared to similar packages like JUMP or NLP models. And perhaps the main one that I really like is the emphasis on a function-based API. So a lot of the time when you're trying to do nonlinear optimization or mixed integer nonlinear optimization, you don't really want to have to define like in JUMP, you don't really want to use macros and things like that, right? You just have a function and that's your objective, or you want to put a constraint on that. And so you having a function-based API is actually really convenient, especially for nonlinear programming. And for the longest time, JUMP, like in JUMP, you had to like splat the inputs and then you had to register the function. And so it was a lot of work to actually just get going with optimizing a function or writing an optimization problem just using a function, even though a lot of the nonlinear optimization packages actually support a function-based API, or they're not exactly incompatible with a function-based API. But because of the way JUMP was doing things, it was a little bit of work. Like in Nonconvex.jl, you can literally define a function and just pass it on to your model and call optimize, and all of this is done in like 5 lines of code. So that's perhaps the first thing, is the focus on the function-based API. The second emphasis here is the use of automatic differentiation by default. So there's actually no way to define gradients and Jacobians right now, or Hessians in Nonconvex, and the only way you can do it is just by defining a custom adjoint rule using Zygote.jl or using ChainRules.jl, which is then picked up by Zygote when you're doing the optimization. And this is also one of the main features that we have actually. And that way, all you have to do really is just define a function that returns an output, and we even take care of the gradients for you. Now, if you want to define your own gradients, you can using chain rules core, but you don't really have to. And it's very easy to actually use other automatic differentiation backends instead of Zygote by defining a custom rule that calls back into the AD backend that you so prefer. So I guess that's the second emphasis of this package. A third one that's still, I guess, in the making, and it's a bit more recent, is the ability to nest algorithms to create more complicated ones. And this is something that we're going to see, at least with multi-start optimization, but there's also a couple more in the making. And so the idea here is that sometimes algorithms are not, like conceptually, they sit on top of each other. And so you should be able to nest algorithms. And that's something that I try to make possible and make easy in Nonconvex.jl. And I guess the fourth feature here of Nonconvex is the ability to handle structs and different container types in the decision variables. So your decision variables do not have to be just like a vector of real numbers or a dictionary of real numbers. It can be like arbitrary structs and data structures, and all the vectorization and unvectorization is done automatically in an AD compatible way. So you can just write your objective and your constraints, assuming that you get the decision input or the input to the function in the structure or in the data structure that you specified as the initial solution. And all the other vectorization magic is done behind the scenes. So installing and using Nonconvex is that simple, and this is really all there is to it, to the API. So just define a model here with the objective function. You can either pass the objective at the beginning or when constructing the model, or you can pass it later. And then you can define some variables with lower and upper bounds, add inequality constraints or equality constraints, specify your algorithm, your options, and then call optimize, right? So it's very straightforward and extremely easy. And here, this is just a normal Julia function, as you can see. So there are a few ways to define your problem, and the one that we saw is just using this model struct, and you can define either one variable at a time or multiple variables simultaneously. And as you can see, we support arbitrary types and container types in there as well. And by we, I mean I. Then you can pass equality, inequality constraints, all that stuff, right? But there's another type of model that allows you to actually pass in named variables. And you can define this directly here as a dict model or dictionary model, and also specify the objective in the beginning or just pass it later. And the really cool thing is you can actually start from a jump model. So this is another feature that was recently added, is you're able to start from a jump model and then convert it to a dictionary model. And all the named variables are taken in and all the constraints are translated to a non-convex dictionary model. And then of course you can add variables, constraints, objectives, and so on and so forth. Right. So for algorithms, we have a whole bunch of them. There's the method of moving asymptotes, there's Ipopt, NLopt, they're all wrapped. There's augmented Lagrangian, which actually wraps Percival.jl, which is an excellent optimization package by the Julia Smooth Optimizers organization. And so you can also use Percival or the augmented Lagrangian, pass on the options and so on. Another really cool feature that perhaps, to my knowledge, doesn't exist anywhere is using this mixed integer nonlinear programming with a function-based API and Zygote as an automatic differentiation backend. So a lot of the mixed integer nonlinear programming packages in Julia can only be used with jump or math opt interface, which a lot of the time locks you into this forward diff or forward mode automatic differentiation if you want. And you have to also use jump for that, or math opt interface, which is not super convenient. And so here you can actually do exactly the same thing, and all you have to change is just change the algorithm and the options, right? And then you get Juniper and Ipopt, or you can use Pavito and Ipopt and CBC for that. So super convenient, same function-based API, nothing really changed. Then we go to multi-star optimization, which comes to the nested optimization algorithms that I was talking about. So here we're optimizing the starting point with some hyperparameter optimization algorithm from the package Ipopt.jl, which is another excellent package in Julia, written by Frederick. And yeah, so you can basically put any sub algorithm here and then have like a multi-star version of that algorithm, right? And in this particular case, we use a GP sampler for sampling points to start from. Yeah, and that's basically everything I have for you today. So please download it, play with it, open issues, discussions, and let's talk some more over how to do nonlinear optimization well in Julia. Thank you.